A continuación, tenemos la conferencia oral de 15 minutos, activación in vitro de elementos retrotransponibles como un modo efectivo de mutagénesis en Musa. Nos acompañará entonces el doctor Eli Khayat, tiene un doctorado por la Universidad Hebrea de Jerusalén, Departamento de Ciencias Vegetales y Ambientales, vicepresidente de Investigación y Desarrollo de Rahan Meristem, con un historial demostrado de trabajo en la industria de biotecnología, profesional de la investigación con habilidades en bioinformática, biología molecular, derecho de patentes, biotecnología y cultivo celular. Bienvenido, Dr. Eli.
Thank you very much. I apologize that I have to speak in English. My Spanish is not good enough. I would like to thank the organizers for inviting us. I will speak on behalf of Rahan Meristem, the company that I've been working for the last 30 years. So the goal of our research recently has been to develop a sustainable TR4 resistant variety. And with this goal, we wanted to emphasize that this variety will be an exportable variety, and therefore we only insisted to work only with a Cavendish variety to cater the export market. So with that in mind, we chose our leading Cavendish variety in the basket of varieties that we have developed over the last few years, and that variety is called Gal. So we've been speaking to a lot of people here, and we had a poster and an exhibit. And many people asked, why Gal? Why not Williams or another variety? Obviously, Gal is a variety that is owned and registered under the name of Rahan Meristem. But that's not the main reason. We wanted a variety that will be useful to the growers, especially a variety that will have good yield, a variety that will have tolerance to stress, not specifically disease stress, but stresses that are due to water deficiency or to heat or other types of stress. And the next objective, we wanted the variety to have a quick return. So Gal has a very quick return. And we wanted also to make sure that it will have a high quality bunch. Finally, we wanted a variety that would be easy to manage by the growers. So if we combine all of these traits, Gal, in our opinion, in my opinion, is the best variety that will be useful for this research. So the strategy that we took is really an original strategy. What we did is we activated certain elements in the genome. Of course, this is a genetic approach. So we activated certain elements in the genome that change the genome, but do not entail any genetic engineering. So this is not really GMO or anything like that. It's legal all over the world. There are no restrictions on marketing this variety and so on and so forth. This was very important in our set of objectives. So just a little background, I'm not going to go into details. In all plant species, there are different types of transposable elements. There are elements of where we know them as class 2 or other classes of elements that have been described for many years now. And there is a subclass of these elements that undergo transcription, translation, reintegration into genome, and by reintegrating into the genome, they create mutations. Now, these mutations are not caused with intervention by genetic engineering. We don't introduce to the plant any nucleic acid. The changes are internal due to the activation of these elements. So basically, the way we do it is we induce these elements to be activated. So the approach is really a high throughput genetic diversity creation. So by using this approach, which is patented for a while now, we have a patent on the approach, on the genetic approach, we create a population of mutants, a very large population of mutants that differ from one another, but the difference is really very, very mild. So there is no big differences between the members of the populations, but each member is slightly different from the rest. Okay, so this is a very good approach, in our opinion, for any plant that is vegetatively propagated. So when we look at the middle of the process, what we want to do is create this approach by doing something that will not really change drastically the genome. And the way we did it is simply by demethylation of DNA. We can demethylate the DNA using a compound in the tissue culture medium, a compound that is called AZA. AZA is a very potent compound that does not allow the enzyme that methylates the DNA to function. So if you look at, one second. Yeah, if you look here, all of these plants originated from the same mother plant. This is the mother plant, and this is a profile of DNA. We used a technique called Southern blot hybridization. So we hybridize a small part of DNA to cut DNA of each one of the plants. So this is the mother plant, and these are successive generations of the mother plant. And as you can see, when we apply the demethylation compound, which is here on this lane, immediately we start seeing changes in the genome, and these are the mutations. Of course, given that these changes are really new elements that are inserted into the genome, it's very stable. We cannot remove them out of the genome. There's no way to remove them out of the genome. It's a physical existence of these elements inside the genome. So using this technology, we wanted to create these mutants. And after we created the mutants, we thought in our strategy at levels of validation that we should use in order to prove, really, before we introduce these plants in the market, to prove that these plants are really resistant to the disease. So what is the evidence? So what are the different levels of validations that we have used? So first of all, one important level of validation is the molecular proof, what I showed you in the gel before. We proved that we can really, we did really modify the genome, not by intervention, not by applying or introducing new nucleic acid, but simply by changing internally the genome. Okay, the second level of validation was by taking the population that we have created. The population was about approximately 10,000 plants, and we used an ex vitro approach. And here I would like to thank the people from the University of Wageningen, Professor Kema and Fernando, who is sitting here, my dear friend, that they have done the work of the selection in the greenhouse. They inoculated the plants, and after inoculation, we could select the plants that were resistant to the disease. The third step in our validation entailed a whole genome sequencing analysis, where we compared the resistant to the wild type based on the DNA sequence. Next step, we performed a field trial. It was not sufficient for us to show that in the greenhouse there would be some, asymptomatic plants, but we wanted to make sure that the plants are fully resistant to the disease. And I emphasize, we wanted full resistance. We did not want tolerance. We did not want plants that will have 20% in the populations that would be resistant. We wanted full resistance, 100% to give the growers. Okay, so we performed the field trials, and finally we performed several field trials in the Philippines, which I will show you the result. And finally, we are now on our way to perform another field trial on the other side of the world in the La Guajira area of Colombia, where recently it was discovered, the disease was discovered. Okay, so the field trials in La Guajira will be in very soon. The plants will be planted in the field. We hope in Q3 of this year. Okay, beyond the resistance validation, we wanted to make sure, as I have pointed out before, that agro-technical parameters are really suitable for commercial production of bananas. So we wanted to make sure that the yield components are really match the gall variety, okay, in terms of number of fingers, bunch weight, cycling time, and so on. And we wanted to make sure that there is proper ripening, the quality of the fruit is good, normal green life, and high Brix value, and so on and so forth. These are all parameters that are very important to the growers. So here, I'm not going to go into details, but this experiment really, this experiment really validated for me that the screening system that was performed at the University of Wageningen was really a good screening system. So our time is short, we will go on. So following the experiment, you can see my photo with Fernando and at the University of Wageningen. From a population of 10,000 plants, we got 415 selected lines that were resistant. We had 2 trials, and the average over the 2 trials was 4.2% of our population showed asymptomatic phenotype. So here you can see the majority of the plants were infected with the disease. Very easy to see, there is no doubt about it. And a very small subset of the experiment, of the plants, were completely and entirely resistant or actually looked asymptomatic. Okay, so then we move to the field trial, and these are the results of the field trial. Excellent result in the field trial, which validated that what we did in the greenhouse was a good system. And so here in the field trial, what you can see, the fruit looks excellent. Actually, it does not look better than GAL. It looks exactly like GAL, no difference whatsoever than the GAL, and all the other parameters as well are exactly like GAL. Of course, the plants, the control, all died and showed strong symptoms of the disease. Another point that I should make is when we did this field trial in the Philippines, each one of the clones that was discovered to be asymptomatic, we propagated the clones and created a population of 120 plants per clone, and we only chose plants that not even one plant will carry the disease or will have some symptoms. Okay, so all of the plants that we took were asymptomatic also in the field. And important to say is that, Yes, it's important to say that most of the clones were surrounded by controls, and the red dots are controls that have died in the field, and these plants really survived the experiment and survived the field. Of course, the field was very, very heavily infected with the disease. There was one person here in the audience that knew the field beforehand, and he told me that it was a disaster when this field, when they tried it. Okay, so this is data on the bunch weight and days from planting to flowering, and you can see that it's not different at all from a normal GAL, which is an excellent variety. Finally, nothing better than a good picture, okay? One picture is worth a million words, okay? So this is the second part of the experiment. On the right side, you see our clones. On the left side, you see the control, which are Williams, and you can tell that it's really 100% resistance. Not even one plant on the right side showed any symptoms, and none of the plants on the left side of the Williams, of the control, showed that it was healthy. Okay, so, for further validation, we went to whole genome sequencing, and we compared the sequence of the genome between a resistant line and the non-resistant line, or the control. And what we discovered was that very close to one of the landing pads of these retrotransposable elements, chromatin-wise, it's really very, very close, 150 kilobase pairs. There is a cluster of resistant genes. It's a cluster of genes. So we don't know if really the effect was over this gene, which is the closest to the mutation, or these other genes, but in any case, it is in the middle of the cluster of resistant genes. This is the data of, these are the data of the whole genome sequencing, whoever is interested in this. Okay, so I'm changing gears, and since it was so successful, I was asked to repeat the same work on a different variety. This time, we decided to cut corners, and what we did with this variety, we planted at the University of Wageningen again. we planted 2 plants in a pot. And we chose only pot that one plant died completely, which was not, which shows that the plant is not resistant. And next to it, there is a complete healthy plant. So this gives us an assurance that our assay is a good assay, and we can continue and take them to the field. Actually, these plants will be planted now in La Guajira in Colombia. And the planting will be also in double. So we will put in each mat, we will put 2 plants, 1 resistant and 1 control. This is the unfortunate photo of La Guajira in Colombia. It's not a nice photo of a banana plantation, unfortunately. And this is the timelines of our next experiment. So this will be done very shortly. Finally, I'd like to acknowledge with thanks the people that helped us in this endeavor. First of all, I would like to thank my team in Rosh Hanikra in Israel. This is the members of the team that did the work. I would like to thank very much Mr. Luis Alberto Restrepo from Banarica in Colombia, who supported this. He's our partner. He supported this research. I would like to thank the people from the University of Wageningen, Professor Kema and Dr. Fernando Garcia, Bastidas, and of course the team that helped them. Also the team from Unifruti in the Philippines that planted in their field, in 2 different fields, in Mcavi and Matsi, in Bukidnon, the Philippines, the area that was heavily infected. And finally, the people that direct our facilities, both in Colombia and the Philippines. Thank you very much.